Thank you everyone for the opportunity to share this paper entitled Comparative Study on Language Models for Task-Oriented Dialogue Systems. And the author for this paper is myself, Vinsen Marselino Andreas, Genta Indra Winata from Hong Kong University of Science and Technology, and the last one is Purwarianti. So the first one should be the introduction. So the task-oriented dialogue system is a dialogue system that aims to do a task and solve a problem. For example, hotel reservation or restaurant booking, etc. Commonly, task-oriented dialogue systems utilize modularized architecture, which consists of NLU, natural language understanding, dialogue state tracking or DST, and natural language generation or NLG. The NLU module acts as a module to understand the intent of the user's input, or understand what is the meaning of the input that user give. And for the second module, the DST act as a tracker of the current dialogue state, whether it's like tracking the topic or tracking what entity is relevant to the dialogue. And the last one is the NLG module, which give response to the user based on the input. Another architecture that can be used to develop a task-oriented dialogue system is end-to-end models. These models aims to generalize or solve the multi-domain task dialogue system, because it can be retrained without changing many components inside of it. Like in the modularized one, we need to change the dialogue system tracking, dialogue state tracking every time the domain change. But in the end-to-end system, we can just retrain with the new data in the new domain. For the end-to-end models, there are two main ideas how to develop it. The first one is to put the knowledge base directly as an input to the models. And the second one is to develop a retrieval module to retrieve the knowledge base, and then augment the result of the knowledge base to the result of the model that generate the response template. Knowledge base here is a knowledge that is relevant to the dialogue system. For example, if it's a restaurant booking, then it's the information about the restaurant. And there's a third idea of how task-oriented dialogue is developed. This one is proposed by Madoto in the paper of learning the high knowledge bases with their parameters for task-oriented dialogue systems. Here they propose how to create a template from dialogues and then embed the template with the knowledge bases. So the steps will be the first one is will be building the lexicalized template. In the image is in the top left where the templates are here. It will create the lexicalized template from the dialogues. For example, here is the any type restaurant, there is name. In the original dialogue, it should be something like any Italian restaurant, there is a name of the restaurant. And after the template is created, it will be lexicalized with the data in the knowledge base. So for example, after the template is created, it will be embedded with the knowledge base here in the table in the middle. Type is Italian, name is Pizza Hut, type is Indian, name is Kohinoor, and so on and so on. So the new data is created, and this new data is used to train the models. In this paper, GPT-2 models are used to train or to generate the dialogue system. So for my research, we use 3 different language models, because the previous one just used GPT-2, but there are also other language models. Also, there are language models that use sequence-to-sequence or encoder-decoder architecture. Encoder-decoder architecture often used in developing a dialogue system because it maps quite nicely from the modularized one. I remember from the modularized one, there's an LU, and it's mapped to encoder in the encoder-decoder. Dialog set tracking mapped to last node of encoder, and then the natural language generation maps to decoder of the sequence model. For the models used here, the first one is BART, a language models developed by Facebook that is inspired by previous language models, which is BERT and GPT. BERT for the encoder and GPT for the decoder. The second one is T5, developed by Google. It's a multi-domain and utilize prefix in its development, where it can receive a prefix to determine what task it will do. And the third one is the sequence vanilla and we use OpenMNT framework to develop it. OpenMNT framework is a framework to create a sequence model, and it is firstly utilized as a machine translation model. So for the methodology here in the graph, there will be two data in the data set. The first one is the dialog data, and the second one is the knowledge base. So the dialog will be, from the dialog, we will extract dialog template and combine the dialog template with the knowledge base to create a knowledge embedded dialog. Then from the knowledge embedded dialog, it will be used as the input and the target of the models, which utilize sequence, BART, and T5. All of this training is conducted in the GPU Tesla V100. And for the dataset, we use Camara's dataset. Camara's dataset is a multi-turn human-to-human dialogue data about restaurant around Cambridge. And because it's a multi-turn human-to-human, we need something to map between because this end-to-end doesn't use dialog state tracking. So we need to put the state of the dialog into the knowledge into the dialog history or the input of the model. So to create the dialog history, we use the user NC token, as you can see in the table. First, for the first utterance from the user, we mark it, or we use user token, and then for the system utterance, we use sys tokens, and so on and so on, until the last one is the user utterance. Then it will be put into the models. For the data, the training data in the original dialog data, there are 676 dialog data, and then it's split to 406 train, 135 valid, and 135 test data. But because of the knowledge embedded method, the training data increased by 9,728. Here's the models that we use. For BART, we use BART base. For T5, we also use T5 base that have 225 million parameters. And for the final sequence, we use two types of models, the small model and the large model. And the detail can be seen in the table with 33 million parameters and 101 million parameters. Here's the result of the first experiment. In the first experiment, we just trained the knowledge embedded data. For the BART, we conduct 4 types of hyperparameter with different batch size and learning rate. And the best for the BART is the second one, which with 16 batch size and 1E-5 learning rate. It doesn't achieve the best blue nor the best F1, but it achieves the balance of both, where, as we see from the first BART, the F1 is so low, and for the third BART, the blue is quite low too. And for the T5, the best one is the fourth one that achieved both best blue and best F1 score. These metrics are used because the blue one shows how fluent the response of the system, and the F1 is the correctness of the entity that is given from the system. And for the best models for each model type, for the sequence small, for the sequence large, and BART NT5, it's shown in the second table. Both BART and T5 outperform the sequence-to-sequence models by quite a large margin, and BART excels in blue while the T5 excels in F1. And here's the comparison of our models with the previous models that is developed. From the for the base, we also achieve better results than the baseline, which is the GPT-2 plus KE, both for the blue and the F1 score in the BART and T5. And for the second experiment, we conduct an experiment where we try to utilize different KB usage or knowledge base usage. The first one is without knowledge base. The second one is putting knowledge base directly into the input, and the third one is the normal knowledge embedded dialog. For the result, the three of them achieve a good blue score, but the BART plus KB is the best one. But for the F1, the BART only or without the knowledge base achieve a much lower F1 score. This is because this one have a hallucination, or there's a wrong of entity, because it doesn't have the information of the entity that's presented in the knowledge base. And to make sure about the BART plus KB and BART plus KE, we also conduct a human evaluation with Likert score in scale of 1 to 5, and the BART plus KE achieve a better Likert score for the human evaluation. Here's the example of each of the models output. For the first one, there's just one question for the input, and each of these models directly suggest a restaurant while the target asks another question. But this direct recommendation is also, I'll check in the knowledge base, it's also right for every models, but it's just recommending directly the restaurant that have expensive price range and in the South Park. But for the second utterance, which already have the Italian food or have the type of the food, all of these three models suggest the same restaurant as the target. The conclusion for this paper is, the first one is applying pre-trained language models improve effectiveness in terms of blue score. Comparing the sequence-to-sequence vanilla with the BART and T5 for the blue score is quite far, and yeah, pre-trained language model helps with the fluency, which depicted in the blue score. And the second one is incorporating knowledge base, improve effectiveness, or reduce hallucination, which is the wrong entity in the right sentence, as shown in the table where the BART or BART in the comparison of BART and BART plus KB or BART plus KE. And the third one is BART and T5 achieve higher score compared to GPT-2, which is the baseline of this paper. I think that's all for this presentation. Thank you.
Okay, thank you, Vinsen, for your presentation. Are there any questions from the audience? I haven't found, oh, yeah, I haven't found any question in the chat room. I probably have one very probably basic question. It's because I don't work with language model, actually. So I'm kind of wondering, how do you compute that Likert score? Because you use it as a measure of your system performance.
Actually, for the Likert score, it's a human evaluation score. So the human will, for each of the answer from the system, human will score it with the scale of 1 to 5. And then it will be, we will count count the mean of the score that's inputted for the human.
Okay, 5 is for when they like it.
Yes.
Okay, and this Likert, is it someone's name or from like?
Actually, it's a scoring method, I believe.
Okay. Our scoring methods for, is it, it's for language model, normally they use it, okay? Is it correct?
Not only for language models, it's for general. Yeah.
I see. This is my, probably I use it, but I don't remember having computing it. Okay, thank you. Are there any other question from the audience? No? If there's no question, I think we can give a round of applause for Vinsen. Thank you for your presentation.